Alright, it is time for kinetics. So kinetics is a fairly math-heavy unit. It's actually a calculus-based unit. So we're not going to be doing any calculus in this unit, but a lot of the equations and the concepts you see are going to be things that you'll also see in calculus. Those of you who are in it now will be taking it next year as well. Just goes to show you that calculus is actually one of the most useful forms of math. It has very, very cross-disciplinary use. Chemistry especially, physics also uses calculus. So we're going to start today by talking about reaction rates. So a little bit about kinetics first off. So we've done 3 different dynamic units in chemistry. The first one was thermodynamics. When we looked at thermodynamics, the big question overall was, does a reaction take place? Looked at Gibbs free energy. If it's negative, that means it's spontaneous. If it's positive, it's non-spontaneous. So it's a simple yes or no question. Then we took a look at equilibrium, and so equilibrium asks us how far does a reaction go. So does it go all the way to products, or is it mostly state reactants, or is it balanced in the middle? We looked at how far a reaction proceeded. Now we're going to take a look at kinetics. So kinetics asks the question, how fast does a reaction proceed? So if you think of like baking soda and vinegar, you mix those together and it starts to bubble. And at first it's going to bubble really, really fast. And then it's going to slow down and slow down and slow down, and eventually it will stop. So kinetics then asks the question is, how fast does the reaction proceed? How quickly does that particular reaction go? Why is it that it starts really fast and ends when it goes really, really slow and eventually stops? So we're going to look at those type of questions for this unit. Anytime we talk about rate, a rate is always something, a change in something divided by time. Okay, like if you talk about the rate that your car moves, you do the change in distance over the change in time. In the case of a reaction rate, we do a change in concentration over the change in time. So there's 3 different ways to look at reaction rates. You can look at the disappearance of a reactant, the appearance of a product, or you can just look at the overall rate at which the reaction proceeds. And it's always concentration divided by time. Okay, so here's a generalized equation. A plus B yields D plus E. And so when we take a look at this reaction right here, we can use it to figure out the rate of the disappearance of a single reactant or the rate of appearance of a single product. So remember, in a reaction like this, reactants react to yield products. So we could take a look at the rate of disappearance of A, because over time A is going to disappear as it forms into products. It's going to get used up. So remembering that rate is always change in something over change in time. So let's take a look at the rate of A. So we use rate subscript A since we're looking at the rate of the disappearance of A. So for that, it would be the change in the concentration of A divided by the change in time, or the time over which that change in concentration occurs. So keep in mind, delta is always final minus initial. And so if we look at the change in concentration of A, so its final minus initial, well, its final concentration is going to be less than its initial concentration because it's disappearing and forming into D and E. And if its final concentration is less than its I, then F minus I is going to give us a negative number. Okay, and we can't have a negative rate. So instead, when we do something the rate of disappearance, we need to say the negative of the change in concentration of A. That way we end up with a positive rate. We can also do this for the rate of appearance of a single product. So as this reaction proceeds, D is going to start appearing. Initially, when we've only got A and B, there's not going to be any D in the system. But as the reaction proceeds, D will start appearing. So then the rate of D would be equal to the change in the concentration of D divided by the change in time over which that change in concentration appears. And that's just a very, very generalized form of the rate equation. So there's a lot more to it than just the change in concentration over change in time, but this is how you would find a general rate over a period of time. Okay, the average rate or the average velocity of a particular reaction. Keep in mind, neither one of these equations are given to you on the test. You need to remember that rate is change in concentration over change in time. And by convention, since rate is always given in a positive number, if we're talking about the disappearance of something, we need to make sure we do a negative so that we don't wind up with a negative rate. And if you wind up with a negative rate, just take the absolute value or multiply it by -1 to get yourself a positive. Okay, most reactions, though, aren't necessarily 1-to-1-to-1. If we've got something that requires balancing, which means there's balancing coefficients in front, it would look something like this generalized reaction. So A, B, B. This right here, the lower, that would be our balancing coefficients. So like a 2 or a 3, something that we put in front in order to balance it. And then A would be our compound or molecule. So whatever is disappearing in this case. So that's what all the lower cases would mean. The coefficients and the capitals would be whatever that compound or molecule is. So if it has balancing coefficients, that means its rate of appearance or disappearance is going to vary. So if we know the rate of disappearance of A, we can use that to figure out the rate of disappearance of B or the rate of appearance of D or E. And we would do it by using this concept right down here. Okay, so you can take out or use any of the pieces of this. So 1 divided by A, which would be the balancing coefficient, times its particular rate, would also give us the rate of B. But in order to get the rate of B, which is the change in concentration of B over the change in time, we would have to multiply it by the reciprocal of its balancing coefficient. And this just shows us that they're going to change by different rates. They're going to have different factors because of those different balancing coefficients. So since more or less of B might be required than A, that means it's going to disappear at a different rate than A. Okay, and same thing with the appearance of D and E. We can look at the rate of D or the rate of E by multiplying it by the reciprocal of its balancing coefficient for either one. And if we had A and wanted to figure out E, it's not like we'd have to go through each process. A, so the rate of this guy would be equal to that guy right there. We could use B to figure out A, or we can use D to figure out A. Anything like that, you can just pick and choose out of this particular reaction. And what's circled in each of these would end up being the rate. And as with the other reaction in the previous slide, or the other equation, this is not given to you on the AP test, so this is something you've got to remember. Okay, you multiply it by the reciprocal of its balancing coefficient in order to figure out what the different rates are. Alright, here's a slide that shows a graph of the concentration of nitrous oxide divided by time. So here's the reaction right here, NO2 yielding NO and O2. So NO2 is going to be disappearing, and at some rate NO will be appearing and oxygen will be appearing. So this graph just shows us the rate of appearance of nitrous oxide. So just that one player right there. And we can see that it starts at 0, so initially we only have nitrous oxide. And at first, wow, it's a really steep curve. So that means it's appearing really fast, and it starts slowing down. And it's appearing at a slower and slower rate until eventually it will flatline. And we're producing no more of the NO. So this is just like that vinegar baking soda equation we were talking about. At first it goes really fast, and then it starts slowing down and slowing down and slowing down until it eventually flatlines. So this is why it's not so simple as just changing concentration over change in time. Because if we look at this and we were to figure out what the rate is, well, the rate is constantly changing. Every second that goes by, every millisecond that goes by is going to change the rate of appearance of NO. So if we wanted to figure out what the instantaneous rate is, so like for this little point in time right there, well, what's the rate of appearance of nitrous oxide at that flash frame of time? In order to figure out, we'd have to figure out the slope of the tangent. So since this is a curved graph, we can't just get our normal slope of rise over run. We have to take a tangent line and look at the slope of that right there. So that slope of that line is going to tell us what the rate is at that point right there. So what rate is it appearing right there at that point in time? Because if we slide over just a couple milliseconds further in time, the rate's going to change. Or if we go back a couple milliseconds in time to right there, it's going to be a different rate right there as well. Right there, right there, right there, right there, right there. So at any point in time, the rate is going to be different. Those equations we looked at before, it's just going to be the average rate. So the average from this point to this point. Okay, but it doesn't tell us much about each step along the way. And in order to do that, we're going to have to integrate the rate at which it disappears or appears. So let's put in the other players then. So NO2 is going to be disappearing, and NO and O2 are both going to be appearing. So we can take a look at this little rate right there. So initially we're starting with just NO2, and at first it's going to disappear really, really quick, and then eventually flatline out. Okay, so it's going to stop reacting, stop producing NO and O2. And if we take a look at NO and O2, they're appearing at the exact same time, but you can see that they're appearing at different rates. Okay, so at the end, we don't have the same line for NO as we do for O2. And that's because if we look up here, there's 2 NOs for every 1 O2. And so their rates are going to be different. And if we take a look at this one, it's almost double what it is for O2. But since NO2 and NO are both balanced at 2, we can see that their rates are the same. The difference is that this one's going to be a negative rate, and this one's going to be a positive rate, because this guy is disappearing, and that guy is appearing. But they're disappearing and appearing at the exact same rate. O2 has a different rate because it's balanced at a 1. So this means at any given point in time, half as much O2 is being produced as NO is being produced. So for every 1 O2 that's produced, you're producing 2 NOs. And so that means a doubling in its rate. So once again, we can look at this and we can figure out what the average change in concentration is for any of these guys, but it's just going to give us an average. In order to figure out what the rate is at any point in time along this line, we're going to have to use some different math, some calculus. So let's take a look at just kind of what's happening during this reaction. So we're going to use another general equation. In this case, we have AB, molecule AB, which is right here. So it's an orange and a blue stuck together. So AB is decomposing into A2 and B2. So if we say that A is the orange ones, like that, and that B is the blue ones. Guess that makes sense. So then if we take a look at all those molecules down there, we have nothing but ABs at time 0. Okay, so when time is 0, so this is the initial time, starting time, all we have is ABs in the system. Then time proceeds for about a minute, so 60 seconds. So here's our initial time, 0, and our final time, 60 seconds. At the final time, we have some AB left in the system, but we also have some A2s and some B2s that have been created. So as this reaction proceeds, you're going to get that curve. So A2 and B2 are both going to be appearing at rates, and they're going to be appearing at the exact same rate because they're 1 to 1. But then AB is going to be disappearing, and so it's going to give us a curved line. So that's important to remember that AB is going to be disappearing, and BA is going to be appearing at a not so steep graph. Or I'm sorry, A and B are going to be appearing. What we're going to figure out now is the average rate at which they appear or disappear. So we're not going to be looking at any given point in time. We're just going to be looking from here to here at the end. And if we look right here, it's given us the concentration. So initially we have 0 A2 and 0 B2 and 15 molar of the AB. After 60 seconds, we have 5 molar of AB left, and we now have 5 of A2 and 5 of B2. So first, let's take a look at the rate of disappearance of AB. So at what rate does AB disappear? So once again, the rate of AB is going to be equal to the change, negative change, because this is a disappearance, of the rate of AB divided by the change in time. So remember, change in is final minus initial, so the final concentration of AB was 5. It was 5.0, but I'm going to run out of room if I write all that in. So 5.00 molar minus the initial, which was 15 molar, so 15.00 molar. And we would divide that by the change in time, so the change in time would be 60 minus 0, so that would be 60 seconds. So over the course of 60 seconds, the concentration changed from 15 to 5, and so the change in concentration would be that. So it's going to be a 10, a negative 10, so a positive 10 divided by 60 seconds. So that means that the rate of AB is 0.1667. And what are the units going to be for this? Well, since the top guy is the concentration, so that's molar, and the bottom guy is seconds, time, that means our units would be molar seconds. So it's molarity per second. That means over the course of 60 seconds, on average, AB changed by 0.1667 moles, or molarity, moles per liter, every 1 second that went by. Let's take a look at the rate of appearance of A2. So what rate does this guy right here appear? So we can't just think of it necessarily with stoichiometry. Right, you can't just say that, okay, 0.1667 moles per second, that means this guy appeared at 0.167 moles per second. It's going to be a little different because we've got the 2 and the 1. First off, let's just do it like we did up here with the rate right there. So we're going to say that the rate of A2 is going to be equal to the change in the concentration of A2. No negative, because in this case it's appearance. So it's going to end up being positive anyway. And we started off with, or ended up, final minus initial, so we ended with 5 molar. And we started with 0, so 5 minus 0, and it also took place over 60 seconds. So that means it's going to be 5 divided by 60, that's 5 molar, divided by 60 seconds. So then the rate of A2 is going to be 0.0883 molar seconds. Sorry, I'm having a little bit of trouble with my pen. That's 0.0883 molarity per second. All right, so we can see that there's 2 different rates here. So the rate at which AB disappears is not going to be the same as the rate at which A2 appears because of that balancing ratio. But we can actually use that balancing ratio to figure it out a different way. So remembering then that the rate of A2, so it would be 1 divided by the balancing coefficient, so the reciprocal of the balancing coefficient of the rate of A2 would be equal to 1 over 2 of the rate of AB. So if we were to figure out up here, like we did, the rate of AB, and we knew that it was 0.1667 molarity per second, we could figure out the rate of A2 because it would be 1/2 times 0.1667 molarity per second. And that means it would be 0.08335 molarity per second. Sorry, I'm having a lot of troubles with this pen down at the bottom of my screen, but that's 0.08335 molarity per second. So just a little bit more accurate number. The difference of 0.000005 is due to a round-off error from rate AB. So, but roughly they came up with the same number. So be prepared to find a generalized rate with either one of these techniques, whether it be just the rate, the change in concentration over change in time, or using this relative rate law right here.